All right, good morning. I see some people signing on like crazy, so that's good. Chapter 3, this is where we start. I hope that you grabbed the notes packets before we went to distance learning. If you didn't, then two things you can do. You can either go into the black folders that I have on Schoology that have the printables in it, and you can print one out yourself. Or you can just use note paper, but if you use notebook paper, I'm going to warn you to try to be really organized when you're doing that. You know, write down which section it is and all of that good stuff as you go through there. And the test that you took yesterday, we did have somebody that was sick, and so they didn't get to take the test yet. I'm guessing it's going to be over the holiday break before I can start on those tests, because yesterday my desktop computer crashed again. You might notice it looks a little bit different on the smart board here. Bear with me, it works a little bit different. It's all supposed to be updated and fixed now and good to go. So we are going to start chapter 3, which is exponential, logistic, and logarithmic functions. And we've got a picture of a band playing here. The loudness of a sound we hear is based on the intensity of the associated sound wave. The sound intensity is the energy per unit time of the wave over a given area, measured in watts per square meter. The intensity is greatest near the source and decreases as you move away, whether the sound is rustling leaves or rock music. Because of the wide range of audible sound intensities, they are generally converted into decibels, which is something that we're going to study, which are based on logarithms. Now, in the chapter, we go beyond basic algebraic functions that we've been studying, polynomials, rational functions, and power functions with rational exponents. And we look at 3 families that are called the transcendental functions. I've always loved that word, transcendental. They go beyond the basic algebraic functions. So we're going to look at exponential functions, logistic functions, and logarithmic functions. And those were 3 that were, again, part of our 12 basic functions. So exponential and okay. So let me do this, since it won't let me go any farther. Exponential and logistic functions and their graphs, exponential and logistic modeling, logarithmic functions and their graphs, properties of logarithmic functions, and then equations, solving, and modeling, and the mathematics of finance. We end with that in this chapter. Now, section 3.1 that we're covering today Section 3.1 that we're covering today is exponential and logistic functions. And it was one of those sections that we originally thought we could complete in 2 days, but it's taken 3. So this is another one where we only have 2 assignments, but you'll just have to do the assignments until you get the feeling like, hey, I don't think we've covered that yet, and then kind of cut off from there. So our goal today, we definitely want to be able to write and use exponential functions. We won't be talking about the logistic today. Graph and transform exponential and logistic functions. Again, we're going to keep that to exponential for today. Hopefully, we'll get to the point where we're talking about the natural base E, Euler's number, and then use exponential and logistic functions to model population growth. That is going to have to wait. So, exponential functions. Let A and B be real number constants. And exponential function in x is a function that can be written in the form f of x equals a times b to the x. Now, notice where the variable is at. It is an exponent, so it's called an exponential function. And I know that kind of seems like a duh moment, but in a little bit they're going to ask us to identify these. And we have to know whether or not they are exponential functions or not. So A is non-zero, because, well, this would just be the x-axis if it were y equals 0. B is positive, We're going to stick with that for a while. And b is not equal to 1, because multiplying by 1 to any power is just multiplying by 1, and there's nothing fun about that. The constant a is the initial value of f, the value at x equals 0. So this part, maybe that'll come back to you a little bit from when you studied Algebra 1. With exponential functions, we always have a nice, easy, ordered pair that we can graph, and that's 0a. And then b is, of course, the base. And we're saying in the ones that we're going to look at right now, we're going to focus on positive b values, positive bases. So, again, notice where the x is, where the variable is, because example 1 has us identifying exponential functions. So we're supposed to determine whether each of these is an exponential function. If it is, then we're going to give them that initial value, so 0a, and we're going to tell them what the base is. So I take a look at a, and I realize, well, yeah, this is perfect. I've got a base, and I've got an exponent. Wait a second, where's a? Well, if there is no number out in front that they multiplied by, that meant it was a 1. So this is a yes, and 0, a, which is 1, and then I have a base of 3. Right there. So, and I wrote on the top of this other problem, and it looks like I'm going to have to reorient the board at some time because when I graph later, this is going to be goofy. So here's what I'd like you to do. I would like you to go ahead and do B, C, D, and E, and then I'm just going to ask you to unmute and help me out with those. That'll give me a chance to orient the board. If anybody needs more time, please unmute and let me know. Can somebody unmute and help me out with B, please? So the first part of this is it an exponential function? Waiting for somebody to unmute and tell me what they know about B. So I'm going to have to call on people today. That's a bummer. Thomas, can you unmute and help me out with B, please?
I said it wasn't a function.
You are absolutely right. Our variable is not the exponent. So you got the easy one there, Thomas. It's a no when you're done. All right, then I need to hear from somebody about C. Natalie, what did you do for C?
I said it was.
It is. So what did you get for what did they call it up there? The initial value.
0, negative 2.
Excellent. And what's the base?
1.5.
It is, thank you very much. So then we get to D. And D, I'm going to go ahead and go over this one because this one was maybe a little tricky. And as you look at it, you realize, well, this is just supposed to be an X right here. That's not just an X, it's a negative X. Well, that means it's not simplified yet. So in order for us to figure out all of the things that they want us to do here, we have to simplify that first. And that means we have to remember that this negative exponent is for reciprocals. So that 2 would become 1/2. Now, it is an exponential function. We still have an initial value. That's going to be 0.7 because that's our A value. But the base is actually 1/2. So we have to watch for that. That's kind of a little trick that they're going to do here. Now, this one, E, I'd rather take a volunteer for. So, is there somebody that wants to volunteer and give me what they thought was going on in E? Nobody's feeling that confident about these this morning, huh? Well, pi, it is a constant, depending on what you are what particular subject in math you are talking about. So this is not a variable, and we would say no. Now, we want you to know that for calculus, which is obviously pre-calculus is taking you there, pi is considered a constant. And the argument is, well, if it's not a constant, well then what is it? We don't know where it ends yet, but that doesn't make it a variable. It is still just a number. So if pi is a constant and it's just a number, then yeah, it's not a variable. There is an argument in math theory that says, yes, pi is still being computed because it is, but it's not going to change. It's still pi. So that one does not have a variable in there. Now it worked. Okay. One way to evaluate an exponential function when the inputs are rational numbers is to use the properties of exponents. So we have to remember how all of those work. Computing exponential function values for rational number inputs. And the first one simply says f of x equals 2 to the x. Basic exponential function. If you think about it, it's the first positive integer that we could think of for exponential growth. So our base is 2. And it says find f of 4, which would be 2 to the 4th. And if you didn't want to use a calculator, you'd write it out. And then do the math. Most people have memorized that 2 to the 3rd is 8, and then they can just take that times 2 more and get 16. Then, for b, we have f of 0. Well, anything to the 0 power is just 1. For c, we have f of negative 3. So hopefully that brings up memories of working with exponents. And you remember, oh, that's right, negatives, those are for fractions, for reciprocals. So what we really want is 1/2 times 1/2 times 1/2. Or you could say, since this is pure division inside the parentheses, and remember that whenever there's pure multiplication or division inside the parentheses, we could actually distribute that exponent of 3. Either way, we get to 1/8, and there it is. D tells us we want a power here of 1/2. Now what that's supposed to bring up in our memories is, hey, wait a second, that's for square roots. So this is really the square root of 2, which, if we grab the calculator, and we went to 3 decimal places, there's there's that 1.414 that we've seen enough now that hopefully when it pops up, we kind of go, wait a second, I think I know that one, you know? So there's that 1.414. And then for E, we have f to the negative 3 halves. So that's going to be 2 to the negative 3 halves. So with this one, there are a lot of ways to work through this one, and there is no specific, hey, let's start with this. But usually, if people are going to make a mistake on a problem like this, it's because of the negative. So the first thing I would do is change that to 1/2 to the 3 halves. Well, now, since this is pure division in here, that means I can distribute the 3 halves to both of them. So pretty obviously, my work becomes about the denominator, because 1 to any power is still going to be 1. So now I have to figure out, well, what do I want to do with that 2 to the 3 halves down there? Well, there's 2 ways to do it. We could do 2 to the 3rd is 8, and then take the square root, because we have that 1/2 power there. Or we could do the square root of 2 raised to the 3rd power. Doesn't make much difference. I think I'll go with 8 and the square root. Well, then we'd want to simplify that, because that's the square root of 4 times the square root of 2, so that'll be 2 square roots of 2. But then we'd remember, oh yeah, we're not supposed to leave radicals in the denominator. So I'm going to have to multiply by the square root of 2 on the top and the bottom of this function, so that I can get the square root of 2 over, and then on the bottom I'll have square root of 2 times the square root of 2 is the square root of 4, so that'll be 2 times 2, which is 4. But if we were going to use this for something in the real world, we probably would have just stopped right here at 1 divided by the square root of 8 and punched it in. So 0.354 to our 3 decimal places. So both in the radical form and as a decimal. Now, this one switches gears and says, well, what if they give us irrational inputs? So irrational inputs are those, well, pi square roots that when you find them on the calculator makes it look like they end because it only goes to those 10 decimal places. But in reality, they are still going strong on a computer somewhere, and there is no pattern that they can find in them, and they don't stop. So irrational inputs, well, we just turn that over to the calculator. So we would go ahead and punch in 2 to the pi. And we would punch in 2 to the square root of 3. And I'm sure you're as sick as I am of having to go back and forth to that calculator, so I will just tell you that to the pi, it's going to be 8.825. And to the square root of 3, it will round to 3.322. So we can still find them. Pi and the square root of 3 are still real numbers, and we can figure out what they are. It's just that the best we're going to be able to do it, because we can't use all of our properties that we had for our exponents, is just grab a calculator and tell somebody, hey, here it is. So now, we had another chunk to our objective that said we had to be able to write these. And the good news is that basic exponential functions are just not that difficult to write. So finding an exponential function from its table of values, and that's what we see over here on the left-hand side, Determine formulas for the exponential functions g and h, whose values are given in table 3.2. How do we find the initial value in the base given a table? So while we're at it, I want you to take a peek at these graphs. Because I hope that brings back some memories and you remember basic exponential growth and exponential decay. And that's what you dealt with back in Algebra 1. So we've got these table of values, and this one is labeled g of x, and this one is labeled h of x. And our job is to figure out how would this be written. Well, we think back to what we were doing before when it said identify them as exponential functions or not. And the initial value is always 0a, and we realize, oh, wait a second. So if I want to know what a is, all I have to do is look at the table and see what they got when they put a 0 in. This one was a 4. And h of x was an 8. Great start. Well, now all I need to figure out is what was the base. And remember, the base had the exponent of x in it. So that meant every time that we put a new integer in there, we were going up or down by the same value. And that same value is the base. To go from b to the first to b squared, you think about, well, what do I have to multiply that by? Well, I have to multiply it by b to the first. I mean, that's kind of a silly question. So if you look at the table, they kind of helped us out here. They showed us that to go from 4/9 to 4/3 to 4 to 12 to 36, you're always multiplying by 3. That's the base. And then we need our little exponent. So in h of x, again, they're helping us out a lot here. We notice, hey, this one's going down this time. Well, the way that that happens is if it's exponential decay. And to be exponential decay, the base has to be a fraction between 0 and 1. And that's what's happening here. So, in the future, if they don't give you that, it's not the hardest thing in the world to find. Because all you would have to do is take any of these as they're in order, because we definitely want to see that it's going by integers in the x table, and divide to figure out what they're multiplying by. 36 divided by 12 is 3. 12 divided by 4 is 3. 4 divided by 4/3 is 3. With this one, 1/2 divided by 2, going to be 1/4. 2 divided by 8, 1/4. So again, you can think about that opposite, that inverse function that we need to make happen in order to see those. So it's not too hard to write these, at least not without any transformations or anything on them. Now, next up, we have extra example 3. And this one's a little tougher. What if the initial value and the base aren't obvious? I don't see a table. All I see is a setup. Find the exponential function f of x equals a times b to the x, whose graph goes through the points -2, 10 and 2, 1/3. Okay. Well, I have two unknowns. I don't know what a is and I don't know what b is. If I have two unknowns, I'm going to need two equations so that I can work those together somehow, hopefully by some basic substitution, to figure out what I really have. So let's see here. This is x, and this is y. But I have two of those, so I'll use that as x sub 1 and y sub 1. And this one as x sub 2, y sub 2. And I'm just going to use my little exponential model to figure out where these things need to go. So we remember, oh yeah, this is y. Now, that's a capital A. It really shouldn't be, but if we put a lowercase a in there, then sometimes people got confused about what was going on. So we decided with an uppercase A, this way it'll kind of stand out and make you think, okay, I've got to find that. I have to do that first. So with -2, 10, it will become 10 equals a times b to the -2. Oh, wait a second, b to the negative 2, I don't think I want to leave that. 10 equals a times 1 over b squared. So it'll really be 10 equals a over b squared. That's probably going to be a little bit more helpful when I get to all the rest of this. Now let's look at the second one. This one would say 1/3 equals a times b to the second. So I start thinking, gosh, I'd really like to use substitution here because, I can't really use elimination, which would be adding or subtracting these two and seeing what happens. This is almost, my red one is almost solved for a. If I could just get that red one solved for a, then I can substitute in. And all it takes is multiplying both sides by b squared. That was pretty slick. So, now we'll substitute that into this one. Oops. I want to keep it color-coded. And I realize, well, I can figure out what b is. Once I have b, I can come back here to my red equation and I can figure out what a is, so I better go after that b first. So 1/3 equals 10 b to the 4th. All right. Well, normally we'd say divide by 10, but this already is a fraction, so how about we multiply both sides by 1/10. So 1/30 equals b to the 4th. Now I need b, so that would mean I have to take the positive and negative 4th root of this thing. To get b. Okay, so there's b. Now I have to use b to figure out what a is in my red equation. So we have 10, and then we're going to take b and we're going to square it. That means I'm not even going to bother writing down the plus or minus. Since we're going to square it, it's all going to be positive anyway. Yeah, that's too squished. All right, so now we have 10 times the quantity, the 4th root of 1 over 30 squared. Okay, wait a second though. So that'll be 10, and 4th root is like 1/30 to the 1/4, and now I have to square that. So power to a power means we can just multiply. So 1/4 times 2, that'll be 2/4, which is 1/2, which is square root. But the square root of 1 is just 1. So we get 10 times 1 over the square root of 30 equals a. Well, slap a 1 under there, top times top, bottom times bottom. All right, we can now write this. We know what a is and we know what b is. So way back at the top, I'm trying to remember if it said f of x. It did. So there's our a. Here's our b. And we might as well write that as the 4th root of 1, which is 1, over the 4th root of 30, so at least we're consistent, to the x. Now, at this point, I hope you're saying, okay, Cedarholm, that's a big mess, because we're not supposed to leave square root of 30 down here. We should be multiplying the top and the bottom by the square root of 30 to try to get rid of that and everything. And this is the fourth root of 30. That's even worse. But with this one of the things that our calculus teacher, Mrs. LaRue, wanted us to show you is that sometimes when you're taking the calculus exam, problems like this end up being in the multiple choice section. There are two sections to those AP Calc exams. One is free response, where you have to basically show all the work and all the steps, and the other is multiple choice. And a problem like this, she said, is going to show up on the multiple choice portion. But you're going to do all this good math, and you're going to get down here and look at this and say, wait a second, that's not one of the answers that they have there. So how do I figure out what they really want? And you'll look down at all the answers, and you'll see that instead of having all these radicals in here, that they have changed this to fraction powers. So what they will do is they'll say, all right, this is really 10, and this is on the bottom, so it was a reciprocal, which means it had a negative power, and it was square root, that's the 1/2 power, so this is 30 to the 1/2 power, and this is really 30 to the, oh, and I forgot my negative, I said it and didn't write it, 30 to the negative 1/4 power to the x. Well, then we take the power to the power over there, and get 30 to the negative 1/4 x. And then we realize we have two similar bases here of 30, and when you multiply similar bases, you add their exponents. Oh, this marker is so thick. So this is going to look a little large for an exponent, but I want to make sure you can read it. Negative 1/4 x minus 1/2. And that would actually be one of the solutions that they have in the multiple choice problems. So this one, definitely a little bit more of a challenge than what we were talking about with those tables, just figuring out what A and B values are and going from there. And we're not going to give you a ton of these, but we want you to at least experience them now, so when you get to calculus, you don't think, oh my gosh, we never did anything like this when we were in pre-calculus. So, ooh, we did give you the whole page for that one. So next up, this is what we were doing before we got into that heavy hitting problem right there, and it was using table of values to write these. So values for a general exponential function f of x equals a times b to the x. As you go up by the integers in the x, which we see right here, you'll notice that every time you're increasing that b by 1. And that makes sense because we're going up by the integers here, which would be by intervals of 1. And again, we can just use 0a to figure out what that a value in the front needs to be. If we have to, we can use division to figure out b, if they don't give us that. So this pattern leads to the following recursive formula for exponential functions. So recursive formula, I hope you remember that from Algebra 2, was talking about how you would explain to somebody, hey, if I have a for an answer, how do I get to ab? What do I do to get that next term in the sequence? And that would be, hey, I'm going to multiply by b. So you just continually multiply each term by b to get the next term. Exponential growth and decay. For any exponential function f of x equals a times b to the x and any real number x, if you need the next term, so not f of x, but f of x plus 1, all you have to do is take that base times what you had for an answer for y. And that recursively explains what's really going on in this table. You just keep multiplying by b. If a is greater than 0 and b is greater than 1, the function f is increasing. And the base is, oops, wrong one, an exponential growth function. So a is positive, b is a number bigger than 1. If you're multiplying by a base that's bigger than 1, you're going to experience exponential growth. If a is greater than 0, but your base is less than 1, so it's a fraction between 0 and 1, because remember, we already said our bases are going to stay positive, so fraction between 0 and 1. F is decreasing, and that's an exponential decay function. Now, special names for b when we are talking about exponential growth and exponential decay. The base b is the growth factor for exponential growth functions, and the base b is the decay factor when you're talking about exponential decay functions. That's another thing that was talked about in Algebra 2. Give you time to get what you need off of there, and then we will start talking about more detail with our exponential growth and decay functions. Let me know if I move this up too fast and you still need to write something down. So exploration 1 has us using graphs of exponential functions, and it says graph each function, and it gives us a viewing window there. Now you're welcome to do that, but these again are review from both Algebra 1 and Algebra 2. So my hope is that you look at y sub 1, y sub 2, y sub 3, y sub 4, and you're saying to yourself, well, those are all growth functions. So when we graph those, they're going to look like this. Now, the steepness of each one is changed by having a larger base. So starting off with 2, that's basic growth. 3 is going up a little bit faster. 4 is going up even faster yet, I should say. And then 5, even faster yet. So they ask us which point would be common to all 4 of these graphs. And you realize that no matter which one of these you're talking about, it's going to go through 0a, and a for every single one of these is 1. So for all 4 of those graphs, because they're so basic, they're all going to go through 0, 1. Now, with this in mind, that little sketch there in your mind, it says analyze the functions for domain, range, continuity, increasing or decreasing behavior, symmetry, boundedness, extrema, asymptotes, and end behavior. So let's get started. When you're thinking domain, think about the x's and think, well, is there any x value that I could not put up in there for x? Well, no, this graph is going to go left and right forever. It's not going up and down forever. The range. Well, when we study exponential growth and decay functions, we find out that the x-axis is actually the asymptote for this graph. It approaches it, but it never quite gets there. Now, here's how that works. So as we raise this to more negative integers that are further to the left on the number line, we're going to be changing this to 2 to the negative 1, which would be 1/2. Then 2 to the negative 2, which would be 1/4. Then we just keep going, so 1/8, 1/16, 1/32, 1/64, 1/128th, and we realize I'm never getting to 0. I'm getting super close to it, so close to it that the human eye is not going to be able to tell the difference. But I'm not going to get to 0. So it's from 0 to infinity, not including the 0, which means we have to have parentheses there. Continuity, yeah, this graph is continuous. Oops, spelling of continuous. C-O-N-T-I-N, missed an O. There we go. All right, next up was increasing or decreasing. Well, this is exponential growth, so it's always increasing. So we'd say it's increasing, and then we would give the interval over which it's increasing, which is the x's from negative infinity to infinity. Doesn't have any of that symmetry, that even or odd symmetry. In fact, doesn't have any symmetry, but we're supposed to just focus on even and odd. Boundedness, we'd have to say no, because that means that it's bounded above and below. We can see that this graph is bounded below, but it's definitely not bounded above. We don't get any local maxes or local mins. We do have an asymptote, and that asymptote is the x-axis. So we get a horizontal asymptote of y equals 0, and then I have to fit the end behavior on here somewhere. Limit as x approaches negative infinity. Oh, they just called it y. Well, we need to use function notation, so we'll use f of x. And limit as x approaches infinity for f of x. So as we go to the left forever, this is going to approach our horizontal asymptote, which is 0. And as we go to the right forever, we can see, hey, this thing is growing big time. Gonna go up. So that's infinity. So really, this is the same thing that we had when we wrote down our 12 basic function papers. You had a worksheet and you went through all of those. What we didn't focus on necessarily was both exponential growth and decay. So as we look at the second box here for the exploration, we see, hey, these all have those fractions between 0 and 1. And that means these are going to be exponential decay. Now, we've got 1/2, 1/3, 1/4, 1/5, and it says which point is common to all 4 graphs. Can somebody unmute and help us out with that? Which point will all of these have? Sydney, you're trying, but all I can hear is squelch. Doggone it, so your audio is not good today. They are all going to have that 0, 1. And then again, we are supposed to analyze these. So, in our head, we want to envision that basic exponential decay graph. And we realize it's going to share a lot with the analysis that we had for exponential growth, but obviously certain things are going to be different. So, domain. Well, we can still use any x. Range. Well, again, we have to think about the fact that the x-axis here, that doesn't look much like an x anymore, the x-axis over there is going to be the asymptote. So we're going to be from 0 to infinity, and these are all with a positive a value because we had a 1 for a. It is continuous. We're not lifting up pen or pencil to draw that graph. And this one is decreasing over its domain. Symmetry, still none. Boundedness, still a no. It is bounded below, but it's not bounded above. No local maxes or local mins, so extrema none. We do have that horizontal asymptote of y equals 0. And we can explain the end behavior. Again, let's call this one g of x. So once you have that written down, can somebody unmute please and tell me as we go to the left forever what our limit is?
Infinity.
It is infinity. Thank you. I probably better change colors so that stands out. Okay, not using blue. And then if somebody could unmute, please, and tell me about as we go to the right forever.
0.
0. Horizontal asymptote of 0. So just about everything that we've done so far has been reviewed, whether or not it's from previous math classes or even when we went over the 12 basic functions. And that gets us to our box up here that has all of that. Do remember, yes, I'm going to try blue again, even though it's been failing me today, that we should put the arrows on there. They do go forever. So domain is all reals, range 0 to infinity for both of these. They are continuous. We don't get the symmetry of even or odd. They're bounded below, not above, so they're not bounded. No local maxes or mins. Again, horizontal asymptote of y equals 0. No vertical asymptotes. We don't have a denominator to worry about. And then, if b is greater than 1, we're talking about exponential growth. And this was the limit behavior that we had, the end behavior. If we're talking about a positive b value, but it has to be less than 1, that means we're talking about b values between 0 and 1, which are fractions or decimals between 0 and 1, and that reverses it. So that's exponential functions. Now what we want to do is take a step towards, okay, what about all the transformations? What does that do? So using transformations from chapter 1, we want to take a look at translations, reflections, stretches, and compressions. And it says describe how to do this transformation, what would it be, into the graph of the given functions, and then sketch the graph by hand and support your answer with the grapher. So we're starting with the basic y equals 2 to the x, and suddenly it becomes g of x equals 2 to the x minus 1. So we have to remember back to our general form for exponential functions, which was y equals a times b to the x minus h power. We better put some parentheses up there, plus k. That'll make it stand out a little bit more. So this means it's going to be 2 to the x translated 1 unit to the right. So what we would want to do is think about that parent y equals 2 to the x and realize, well, that's going to be 0, 1, 1, 2. If we raise it to the second power, it'll be 4. If we raise it to the third power, it would be 8. Up here somewhere. So here's my parent. And all I have to do is take those nice points that I just put on there and move them 1 unit to the right. And there it is. Now, if you wanted to, if you want to be more formal about it, you could make a table so that you could use that for every single one of these. And use that as your parent function. And that was my warning that we only have 1 minute remaining. So we're going to stop there. I don't think you'll be able to finish the day 1 assignment up there. But again, go to the point where you're like, okay, we already talked about this in class. Oh, wait a second, this we didn't do. And then you can stop. Because we will have 2 assignments over 3 days. So you can kind of spread it out a little bit. But what you don't want to do is not do any of it tonight. You know, try to get a little bit of this in your noggin now before we move on to some tougher stuff. That will really help you to have a base for your learning. Have a great day, everybody.